Welcome to OOkul. I welcome you all to this lecture series on basic thermodynamics. This is lecture number 14 on thermodynamic relations. So basically we are inching closer towards the final lectures of this thermodynamics series. So this is most probably the second last video which we am posting. So let us begin this. First of all, we see two functions which are of very much importance. One is known as Helmholtz function and second is known as the Gibbs function. So Helmholtz function is given by f equal to u minus ts and Gibbs function is given by g equal to h minus ts. Please remember these things. Now for any real process, the Gibbs and Helmholtz function decreases and they attains a minimum value. This is the fact about these two functions. So then there's some basic mathematical relations. If z is a function of x and y, then we have dz equal to del z by del x at constant y into dx plus del z by del y at constant x into dy. Let us take this term as m and this one as n. So z is exact. If it is written that z is exact, that means del m by del y at constant x is equal to del n by del x at constant y. Okay, again, if z is a function of x and y, so we can write this as del z by del x at constant y multiplied by del x by del y at constant z and del y by del z into constant x equal to minus 1. Now the Maxwell relations, we derive the Maxwell relations. From the first TDS equation we have TDS equal to du plus PdV, or we can write du equal to TDS minus PdV. So from here we can write as del t by del v, this is del t by del v at constant s is equal to minus of del p by del s at constant v. This is first Maxwell relation. Now from the second TDS equation we have TDS equal to dh minus vdp, or we can write dh equal to TDS plus vdp. So from here del t by del p at constant s equal to del v by del s at constant p. Now from the Helmholtz function we have f equal to u minus ts or df equal to du minus tds minus s dt. So using the TDS equations we have du minus tds as minus pdv here. So df equal to minus pdv minus s dt. So we get del p by del t at constant v equal to del s by del v at constant t. Then the last one from the Gibbs function we have g equal to h minus ts, dg equal to dh minus tds minus s dt. This will be equal to vdp from the second TDS equation. So dg equal to vdp minus s dt. So from here we can write del v by del t at constant p equal to minus of del s by del p at constant t. Okay, but remembering them in this way is a very difficult task. Okay, and sometimes you may get confused and you may get it wrong. So to simplify the task, we have one method that is known as a Tapestry method. From here we will see how to know. You don't have to basically remember these relations, but you can just find them out during the examination as well, just in 30 seconds. See, note down four words from here, that is T, P, S and V. Okay, and write them in this way: T, P, S and V. Okay, so now do one thing. First go this way, then go this way. Okay, and then this, then this. Okay, so when you go from here till here, you have del t by del p at constant s is equal to del v by del s at constant p. This you get as the one relation. For finding out the next one, you have to do it the same way, just change the direction this way. Okay, so del p by del t at constant v, del p by del t at constant v is equal to del s by del v, del s by del v at constant t. Okay, for finding out the third one, now the movement this way, that is del t by del v at constant s is equal to minus of del p by del s at constant V. Okay, and the last one, del V by del T at constant P is equal to minus of del S by del P at constant T. Okay, so these are the relations. Now how to remember that where to use this minus sign and where not to use this minus sign? See, we have for each expression two movements. One is the horizontal movement and another one is the vertical movement. Okay, so just remember, whenever our first movement is horizontal, okay, the first movement is horizontal, then we take the positive sign, okay, like in this and this case. And whenever we have the first move as vertical move, like this, first going this, then turning this way, or first going down, then turning this way, so in these cases we have the negative sign, as in this case and in this case. So basically you don't have to remember from those tedious equations and all, that is the basic method, but this is the trick which can be used in an examination to find out any of the 4 Maxwell relations within 30 seconds or even less than that. So now moving ahead, finding out the tedious differential equations. See this, S, that is entropy, is a function of T and V. So ds equal to del S by del T at constant V into dt plus del S by del V at constant T into dV. Okay, so from the first tedious equation we have tds equal to du plus p dv. Now if the volume is constant, we have dv equal to 0. Why we are finding out dv equal to 0? You will understand it. Okay, because we have to find out at constant volume here. Okay, so tds equal to du and this is equal to cv dt. So we can write from here, that is ds by dt equal to cv by t, or we can also write del s by del t at constant v equal to cv by t. And from the Maxwell relations we have del s by del v at constant t, that is for this term, equal to del p by del t at v. Okay, this you can verify yourself. So just substituting these values, we get ds equal to cv by t into dt plus del p by del t at constant v into dv, or just multiplying with t on both sides, we have tds equal to cv dt plus t times of del p by del t at constant v into dv. Okay, so this is first tedious differential equation. Now moving forward with the second one, on the similar lines we have to do it. That is, S is a function of temperature and pressure, so ds will be equal to del S by del T at constant P into dt plus del S by del P at constant T into dP. So from the second tedious equation we have Tds equal to dH minus Vdp, and if the pressure is constant we can say that dP is equal to 0. Okay, so we have Tds equal to dH equal to Cp dt. Okay, so ds by dt is equal to Cp by t, or del S by del T at constant P equal to Cp by t. Okay, and from the Maxwell relations we have del S by del P at constant T is equal to minus of del V by del T at constant P. So just substituting these values we get ds equal to Cp by t dt minus del V by del T at constant P into dP. Just multiplying by t on both sides we get Tds equal to Cp dt minus t times of del V by del T at constant P into dP. Okay, this is just the mathematical thing. I don't have anything much to explain in this. Okay, so now the mathematical proof of Cp greater than Cv. What is the mathematical proof of that? Let us see. From the tedious differential equations we have both these terms equal to Tds, so just equating them, getting the terms on one side, that is Cp minus Cv dt equal to t times of del P by del T at constant V into dV plus del V by del T at constant P into dP. Okay, so writing dt equal to t by bringing this term down, we get t over Cp minus Cv into this term remains as it is. Now if t is a function of pressure and volume, so we have dt equal to del T by del P at constant V into dP plus del T by del V at constant P into dV. Now from another mathematical relation we have this term, that is del T by del V at constant V into del P by del V at constant T into del V by del T at constant P equal to minus 1. Now comparing the coefficients of dP in equation 1 and 2, okay, just see, compare the coefficients of dP in both the equations, this 1 and 2 equations. You will get T by Cp minus Cv into del V by del T at constant P equal to del T by del P at constant V. So from here we can write Cp minus Cv equal to T times of del V by del T at constant P and del P by del T at constant V. And from the third equation we can write del P by del T at constant V as minus of del P by del V at constant T and del V by del T at constant P. So del P by del T, this side will be equal to minus of this into this. Okay, so this is written here. So Cp minus Cv will become equal to minus of T del V by del T at constant P whole square into del P by del V at constant T. Okay, so this is a minus sign, so this will be negative always. This is the absolute temperature, so this will be positive. This is the whole square, this will also be always positive. And see this one, we have PV equal to RT as an equation. So if temperature is constant, that means PV is constant. So in this case, P is inversely proportional to V. So if we find out the change of any one of them, that is say the change of P with respect to V, so if V will increase, then P will decrease, and if V decreases, P will increases. That means they are inversely related, so that will be always negative. Okay, so just using this, we get Cp minus Cv is positive, or we can say that Cp is always greater than Cv. Okay, so now we'll define one more term, that is the coefficient of volume expansivity beta as 1 by V del V by del T at constant P and isothermal compressibility Kt as minus 1 by V del V by del P at constant T. Okay, so these are two different terms. Then we have one more equation, that is Cp minus Cv equal to Tv beta square over Kt. This equation is known as the Mayer's equation. Okay, and for the Mayer's equation for ideal gas, this Tv beta square by Kt becomes equal to R. Okay, now talking about the energy equations, from the first TdS equation we have TdS equal to du plus Pdv, or we can write du equal to TdS minus Pdv. So from the first TdS differential equation we have this term, that is du equal to Cv dt plus T times of del P by del T at constant V dV minus Pdv. Okay, basically we are replacing the TdS out here and this term remains as it is. Then we get du equal to Cv dt plus T times of del P by del T at constant V minus P into dV. And for the ideal gas we have Pv equal to RT. So del P by del T at constant V into V will be equal to R. Just multiplying by T we get RT by V. Okay, and that RT by V from here is nothing but P. So substituting it here we get du equal to Cv dt plus this term becomes 0. So we have du equal to Cv dt for the ideal gas. Similarly, from the second TdS equation we have TdS equal to dH minus Vdp or dH equal to TdS plus Vdp. From the second TdS differential equation, just replacing this term as this. So we get dH equal to Cp dt minus T times of del V by del T at constant P into dP plus Vdp. Okay, and just taking the dP common and doing it this way. For the ideal gas we have PV equal to RT. So del V by del T at constant P into P equal to R. Just multiplying by T we get RT by P, that is nothing but equal to V. So for an ideal gas we get dH equal to Cp dt because this term gets equal to 0. Okay, next we have the Joule Thomson coefficient. What is that? Joule Thomson coefficient denoted by mu, given as the slope of del T by del P, that is the slope of temperature and pressure curve in a constant enthalpy process. So For the energy equation for the ideal gas, we have dH equal to Cp dt minus T times of del V by del T at constant P minus V into dP. Now if H is constant, then dH will become equal to 0. So we have 0 equal to Cp dt minus this whole term, or Cp dt will be equal to this term. Okay, so dt by dP, that is the slope of this curve, the temperature and pressure curve, equal to 1 by Cp T times of del V by del T at P minus V. So this becomes the Joule Thomson coefficient for real gas. Now for the ideal gas, we have PV equal to RT. So just doing the calculations, we get this term as equal to V. Okay, so for the Joule Thomson coefficient, just substituting it here, we get the Joule Thomson coefficient or mu for ideal gas equal to 0. Now what is that? For the real gases, it looks somewhat like this. These are the constant enthalpy lines. Okay, this is the inversion curve, that is mu equal to 0 at this inversion curve. The regions on the right hand side is having the slope as negative, so they are the heating regions. That means in this case del T by del P is negative. That means, as you can see, as we are increasing the pressure, the temperature is decreasing, or as we are decreasing the pressure, the temperature is increasing. That means this is the heating region. Okay, and in this is the cooling region. The mu is positive. That means when the pressure is increased, the temperature also increases, and when the pressure is decreased, the temperature also decreases. So that is the cooling region. Okay, because this is basically used in the throttling kind of a cases. So in the throttling cases, what happen, or in the expansion cases, what happen, the pressure usually decreases. Okay, so when the pressure decreases, if the temperature is increasing, that is why we are calling it as a heating region, the right hand side of the inversion curve. And for the left hand side, when the pressure is decreasing, we see that the temperature also decreases, because the mu, that is the Joule Thomson coefficient, is positive for the regions to the left of the inversion curve. That is why we call that region as the cooling region. So please remember, in the cooling region, the value of mu, that is Joule Thomson coefficient, is positive, whereas in the heating region, the value of mu is negative. Whereas everywhere on the inversion curve, the value of mu or Joule Thomson coefficient is 0. Okay, now we see for the ideal gases. For the ideal gases, we have already seen that the value of Joule Thomson coefficient is always 0. So it's a straight line which is parallel to the pressure axis. Okay, now some important points. Joule Thomson coefficient is positive in cooling region and negative in heating region. It is 0 everywhere on the inversion curve, that I have already told you. Joule Thomson coefficient is 0 for ideal gas everywhere. Okay, now whenever ideal gas is used as a refrigerant, as air in gas refrigeration cycle, throttling is never used. Why? Because it does not result in any temperature drop. Instead, isentropic expander or turbine is used. Why? Because air acts as a ideal gas, and for the ideal gas we have already seen that mu, the value of mu is equal to 0. So it does not give any kind of reduction in the temperature when we used it in the throttling process. Okay, next is in the vapor compression cycle, throttling is used and not isentropic expander because of economical reasons. Okay, next is we come to another equation that is known as the Clausius Clapeyron equation. Okay, so from the Maxwell relations, we have del T by del P at constant V equal to del S by del V at constant T. Okay, so now for the phase change, we have the pressure is a function of temperature only, because we see that in the wet region or in the phase change region, the pressure and temperature are dependent on each other. So del P by del T at constant V become equal to dP by dt. Okay, also del S by del V at constant T will be equal to Sg minus Sf over Vg minus Vf. This all we are talking in the phase change region. So dP by dt will be equal to Sg minus Sf over Vg minus Vf. Now we know that Vg, that is the volume of vapor, is much greater than the volume of liquid. Okay, or we can write that Vg minus Vf is approximately equal to Vg only. Okay, so now therefore this dP by dt equal to Sg minus Sf over Vg. Okay, so Sg minus Sf is nothing but the latent heat of fusion over T saturation. This we have seen in the previous lecture. So this becomes equal to HFG over T saturation. So we can write dP by dt equal to this Sg minus Sf as HFG over T saturation divided by Vg. This is known as the Clapeyron equation. Okay. Now if the vapor is an ideal gas, then we have PV equal to RT, or Vg can be written as RT saturation over P. So just substituting it in this equation, we get dP by dt equal to LH, that is the latent heat of vaporization, over, in place of Vg, just replace it with this, so we get latent heat of vaporization LH over RT saturation square into P saturation, and this equation is known as Clausius Clapeyron equation. So that's all in this lecture of thermodynamic relations. I hope you are enjoying learning with OOkul. So if you have any doubts, any comments, any queries, any feedbacks, you can write to us in the comment section below, and also you can suggest these videos to your friends, to your colleagues, so that they can also benefit out of it. And if you haven't subscribed to our channel yet, please subscribe for more upcoming videos. We will be very soon launching the videos for different courses as well, other than mechanical engineering, or rather I should say other than engineering itself. So please subscribe to our channel. This is just the beginning of a very big journey. So we are just on the starting phase. We will let you prepare with us for each and every examination. So I hope you are liking the work we are doing for you. Very soon we will be providing you the quizzes and all as well for practice. See you in the next video. Till then, keep learning with us and keep suggesting us the way to improve better. So thank you and have a nice day.